Greetings. Let's say I have this kind of situation when there is this mass of 2 kilograms. I declare the friction of this surface to be 0. Alright? To simplify really much, so simplify the situation. Then there's this pulley wheel carrying on this force, and there's this hanging mass that will basically, thanks to the 0 friction, there's no static friction, no kinematic friction. That means that straight away it will start accelerating over this which I also declare to be waveless of a string that connects these two masses. So thanks to this, the system will start accelerating. And actually, to make it even more visible that this really works for even very low forces from this side, I'll say this mass is actually smaller than the one that it pulls on. But yet, it will work out and it will give an acceleration of this situation. So once again, to explain what's going on here, well, there's this wheel over which goes this string. This mass of 1 kilogram is hanging down, and over this string and over the wheel that carries on all the force without friction, without any losses, the force gets with tension on the rope connected to this other mass which is standing straight on this perpendicular surface. It's a horizontal surface, and this mass has 2 kilograms. It's pulled down by this one, alright? And there's no friction on this surface. That means there will be no resistant force to the motion. The motion, of course, because this mass pulls this entire thing down, it will be towards here, towards the bottom. It will be in the direction of from 2 kilograms to the 1 kilogram thing. Alright, so to determine the acceleration of this system, I will have to use the formula F equals m times a. Again, force equals mass times acceleration. And the thing I have to realize is to first count with the counteracting forces and so on. But what is really interesting and useful in this exact example, I declare friction to be 0. So there's no resistance to the movement over the surface of this mass that is actually laying on the ground here. There's no friction, and actually, it except for its weight force, which is on Earth, let's say around 20 newtons. It can be the acceleration of gravity, the g, which is basically substituted for a, in this case multiplied by m to give the normal force to the ground. It goes straight down. The normal force would point out up in the opposite direction, right? But I don't even draw it here really, although it does exist. But it's not required for this particular experiment to just mention it here. What really is important to just realize that the weight force for this object is 20 newtons down, because the weight is 2 kilograms and the acceleration of gravity that pulls things down and causes this weight force is around 10 newtons per kilogram. Alright, so this one will follow the same rule, but because of just 1 kilogram, I will say it's around 10 newtons. So the weight force here is around 10 newtons. Now, the overall force that causes this motion to happen is actually only this force. It's just only this force. And the reason is because there's no friction on this one. There's no friction with the ground for this one. And this one is the one that's hanging down. It's the one that can freely be accelerating below itself. It can go down and down and down because there's nothing below it blocking it to go as follows. So when I calculated for the acceleration, we started with this formula F equals m times a, and now I want to calculate for a. So I divide both sides by m, I get F over m is a. Now, I have to determine what the force I will use here is, and really it is only the force, the weight force that pulls the, even though it's just the lighter one because it's the one in the air, the one pulling this entire system down because it has the freedom to go down below itself, unlike this one which is just stuck on the ground, waiting for this one to pull it down over the rope. This is the entire net force. There's no resisting force. If there was friction, let's say 3 newtons to the left, because of this one having friction with the ground it lays on, well, the F I would use here would be the 10 newtons minus the 3 newtons. But because here there's friction that is 0 newton friction, 0 force in the opposite direction of this motion, well, I'll just use the 10 newtons and there's nothing else blocking it really. And now, of course, that has to be divided by mass. And division by mass, it's not only division by this one, but to account for the fact that this actually still has to be pulled, I have to mention it. And it's not that here friction was 0 and it was not counted into the force. This thing will already have a footprint on the overall force in case there was friction, but because this case is trivial, there's no friction from it directly, well, the force is not affected by this one. But what is affected is the overall mass. So for the M here, not only do I say it's 1 kilogram, but it's 1 kilogram plus 2 kilograms. It's the mass of this entire system, because this entire system is integrated together. It moves all together, and the acceleration applies for the entire system, for the rho, which is way less compared to all these things, so doesn't get calculated or doesn't get included in the calculation. And also these all things connected together by the rho I all together with the same acceleration. They will be accelerating together and with the same angle. Therefore, the mass of the sum of both has to be used, and that is 1 plus 2 kilograms. Alright, so the acceleration of the system ends up being 10 over 3. Now it's newtons over kilograms, or meters times second to the minus 2. This is the unit that makes more sense as far as the velocity rise, the motion expression. Alright? So this is the result.